Most vision language models process an image using hundreds of tokens. And that's slow, expensive, and inefficient. But what if you could cut that down by 10x without losing performance? Also, what if the problem with vision language model isn't the model, but the tokens you feed into it? This paper completely rethinks visual representations and unlocks a faster, cheaper, and even better reasoning. This paper is called When Lava Meets Objects, Token Composition for Vision Language Models, and they call their model Mask-LLaVa. So all of the tokens, both the text and the image tokens, they live in the same LLM embedding space. And that's a powerful idea, but it comes with a cost. So in the standard Lava architecture, a single image is typically represented by about 576 visual tokens. So if you consider a 336 by 336 image, and if you split that into 24 by 24 grid of patches, you will have 24 by 24 equals 576. But here's the problem. When you're decoding autoregressively, that means one token at a time, that scales poorly when the sequence is really long. So the more visual tokens you have, the more expensive and slow everything becomes. So here's the question. How do we reduce the number of visual tokens without sacrificing the performance? So here's how Mask-LLaVa thought about it. Let's take a step back and rethink how the tokens are represented. So instead of treating all of the patches equal, regardless of what they contain, Mask-LLaVa takes a smarter approach. It introduces a mixed token design, and it combines representations at different levels of granularity and focuses the token space on what actually matters. So this shift does two things. Now you can control the number of tokens at different levels of granularity. So at each level of granularity, you can decide how many tokens you want to have. And you can also preserve a performance under very tight token budget because now you can control the number of tokens. We'll see that later how that control is implemented, but this is the big picture. The authors, they also report that there's an improvement in the hallucination, robustness, and also understanding of fine-grained objects. So this token design is not about just efficiency, but it improves the quality of reasoning. Just a quick note on the earlier work. Yes, they focused on pruning tokens. So this is deciding which patch gets dropped based on attention maps or saliency maps, and also compressing tokens. This is merging similar patches together, but Mask-LLaVa is different. It's not compressing and it's not pruning. It's actually changing the composition of the token set itself. And it's going to introduce something called an object-centric token alongside the patch tokens. So it's reshaping how the visual information is represented at a very fundamental level. Let's take a look at this image. Now, instead of representing this image purely as a dense grid of patch tokens, the idea here is to build something smaller, more structured, and more informative. So let's take a step back and ask, instead of the grid of patch tokens, what information does the model actually need? Because not every patch equally matters. What we really care about falls into three categories. You have the global context, you have certain local details, and you have the object level, for example, the tomato, or the jar, or the apple. Let's zoom out a bit and look at the architecture of Mask-LLaVa. So first, at the highest level, we want a summary of the entire scene. So the model is going to keep a single global token. It's similar to the CLS token. And this token is going to capture the overall semantics of the image. It's a kind of a scene level summary for the LLM. So as the LLM is going to process your patch tokens altogether, there's going to be a token on the side called the CLS token that is going to aggregate and summarize the information across all of the tokens. And so we're going to keep one global token to represent the full image. Second, we're going to need spatial detail. but we don't need every single patch. So instead of keeping all 576 patch tokens, the model pulls them spatially. So think of this as compressing local regions into summaries. So you have the original 24 by 24 grid is 576 tokens. With spatial pooling, these are going to be reduced to 36 local tokens. So these pooled patch embeddings, they're going to preserve the layout and the nearby interaction. So what is happening where, but at a much lower cost. Third, we have object level understanding. So here's the key addition where things get really interesting. Instead of relying on patches, the model explicitly extracts object-centric features. So this happens through a pipeline. You're going to run an object detector, get the bounding boxes, then you're going to track those bounding boxes through time, and then you're going to segment those bounding boxes so you get a tight mask around the object. And each mask isolates a region in the image, and for each of these regions, the model is going to build a dedicated object token. Now, this token is not just the mask-specific features, but it's also the global context, and it's also the positioning. All of them combine to form an object token. So instead of generic patches and somehow infer the object from those patches, we're going to have dedicated tokens corresponding to actual semantic entities in the scene. And also another feature in the paper is that these heat maps that you see right here suggest that these embeddings are tied to localized regions. Meaning if you query the LLM and you give it the embedding and you say light up the part of the image corresponding to the embedding, is going to light up exactly that object as opposed to a vague notion of the object. It's going to be more precise in terms of the localization. So let's summarize a bit. So instead of feeding the LLM a flat grid of patches, now we have a curated visual token set. And each type of token serves a different distinct role. So you're going to have your global token, what the image is about. Right here, you're going to have local tokens. So these are spatial layout and interactions. And we're going to have tokens for each of the objects. And so this is the key shift here. We're no longer asking the model to infer structure from raw patches. We're injecting the structure directly into the token space. So let's zoom in on a key question here. Where do these object tokens actually come from? So as we've said, there's a pipeline. We're going to propose object regions right here. And for each box is a candidate region that may contain an object. And at this stage, we have where the objects they could be. Next, those bounding boxes are passed to segmentation anything model. So Sam is going to convert each box into masks. So this is going to give you pixel level precision for each region. On top of that, we're going to add one extra background image here. So in total, you're going to have 101 masks. You're going to have 100 object regions like this, and then you're going to have a background region. Now the last part is how we're going to turn the mask into tokens. So each of these masks right here is going to have to be converted into a single embedding. But instead of just averaging features inside the mask, the model uses a method called mask inversion. So here's the intuition of mask inversion. Instead of reading features from a region, we optimize the token such that its explainability map aligns with that region. So in other words, let's say we have a query mask right here and we start with step 1. We start with a token. And we adjust it so that the model's internal attention, which you see is diffused, and as we iterate on it, the attention is going to more and more be focused on the object itself. So each object token becomes a localized representation and it's explicitly tied to its region. So you see how we started here being diffused and vague. Since the dog, it also relates to what's next to it or what's around it, but as we iterate, it becomes super explicit. So these object tokens are not just simple averages of pixel features, or they're not pooled representation, they're optimized region-aligned embeddings that explicitly correspond to these segmented objects. So that makes them far more precise and useful when reasoning about distinct entities in the scene. So the way it works is that it tries to optimize a learnable embedding so that the model's explainability map for that embedding aligns with a target mask. So instead of asking what features are inside the region, it asks what embedding would make this frozen VLM attend exactly to this region. At the core, what we're trying to do is we're trying to minimize a very specific objective. We're comparing the explainability map with the target segmentation mask, and we're trying to reduce the mismatch between the two so that the embedding is continuously refined until its attention footprint matches the desired region. Let's talk about norm scaling. So we know we have different types of token. We have the global, the local, and the object entities. How do you merge these tokens when they're coming from completely different mechanisms? So the problem is that they don't naturally live on the same scale. The issue is that these types of tokens, they're produced differently. They come from different pipelines, they have different statistics, and different magnitude distributions. So if you just concatenate them, you're going to introduce bias. So the model might rely on one token type or ignore something else because there's a scale mismatch. So the fix is norm scaling. And this is what the authors they do. So you use patch tokens as the reference distribution. You compute their mean and the standard deviation. And then you normalize the global token and the object token to match this distribution. So now all of the token types, they operate on a comparable scale. So now you can compare one versus the other, and then the attention weights are actually going to treat all of those relatively the same. So before merging everything into a single sequence, the model does one crucial alignment. It calibrates the token space so that different token families can be combined cleanly. And so this is what makes the final representation stable and meaningful. So let's talk about the token budget. So this is one important practical idea in the design. You can change the token budget and inference time without retraining the model. So let's unpack that. Normally, when you train a model, you train it to expect a fixed number of tokens. So we spoke about the image that had 24 by 24 patches, which means it's 576 tokens. So if you train a model on 576 tokens, this is what it's the budget of it, and you're locked into that. But here it's different. The model is trying to say, I can be trained with rich token budget, but I can still function if you give me less. So this means that you can train on a rich token budget, but then at inference time, you decide how many visual tokens you feed into the LLM. So for example, let's say you start with different objects in the image, you can decide to keep the most confident mask based on some IOU-based filtering step. So you can control how many objects, for example, are passed to the LLM. Let's say you're trying to pool different local features. We spoke about how they pooled spatially the number of local patches down to 36 tokens. Well, you can also prune it further to have them reduced. So during training, the model uses 36 local tokens. It uses one global token, and it uses 101 object tokens. So that's a total of 138. But at inference, you can actually reduce this dramatically. You can have 36, 1, and 20. Or 36, 1, and 5. Or you can have Instead of 36, you can have 23 pooled patches with one global token and 5 objects. And here's the key point. The model weights stay exactly the same. It's only the input token set that changes. So why is this important? It's because there's an advantage. If you lower the token count, you can actually lower your inference cost and make latency faster, right? So instead of training separate models for 138 or for 57 tokens or for 29 tokens, you train once and then you choose the budget later, depending on your constraints. So the model has been trained to remain robust under token scarcity. And that's what makes this architecture flexible in real-world deployments. Okay, and lastly, let's talk about how is this trained. So there's 4 stages. Stage 1 is a projector-only pre-training on captioning data. And the vision encoder and the LLM are frozen. Then you have stage 2. And here we're doing instruction tuning, where the projector and the LLM are trained, but the vision encoder is the one that stays frozen. So let's recap this when lava meets object paper. What should you take away from this? There's a few things. Don't rely on raw patches alone. Sometimes mixing the visual representation, choosing tokens at different granularity, it actually makes a bigger difference. In this case, we got scene level context, spatial structure, and explicit object understanding. Another point is train rich but infer cheap. So during the training, we used 138 tokens, but then during inference, we can aggressively reduce to 57, 29, even 15 tokens. And you don't need to retrain the model for different token structures. So here's one thing. When you mix tokens that come from different pipelines, their magnitudes are not going to match. So without normalization, some tokens get overemphasized, others get ignored. So norm scaling ensures that all the token types contribute on equal footing. So the big picture in this is that efficiency doesn't come from removing information. It comes from representing the right information explicitly. And that's exactly what this architecture is doing.